So for those that don't know me, I'm Miguel Rocha. I'm a grad student at UC Irvine, and I work with this great hardworking and smiling people. So I want to start by introducing the SIDM model, since it has been forgotten for some time. And all what it is just our standard beloved lambda CDM with the only addition that dark matter particles can interact with themselves. How strong they interact is parameterized by the cross-section per unit mass. And Miguel Rocha in 2000 pointed out that if this cross-section per unit mass is in the order of 0.1 to 100 centimeters squared per gram, then there will be some interesting phenomenology that could help solve some issues at the small scales for the standard lambda CDM, namely the Cosmological problem and the missing satellites problem. Of course, these days we know there's no missing satellites problems, but as I'm going to show you, SIDM actually for about 1 centimeter squared per gram below actually is really bad at, it's very inefficient at suppressing substructure. So it's actually a good thing. So just to give you an idea how strong these interactions are, 1 centimeter squared per gram is about a barn per giga electron volt, which is just nuclear-nuclear interaction cross-sections. So these interactions are as strong as interactions in the strong force in the standard model. So these are huge cross-sections. So is this crazy to expect that dark matter has these huge interaction cross-sections? It depends who you ask. For astronomers, for us astronomers, it looks kind of exotic, simply because we believe, that the most probable candidate for dark matter is WIMPs. So WIMPs don't predict self-interactions at all, so any model that predicts self-interactions is exotic. For a particle physics, it's not really that exotic. It's actually a generic consequence of many models beyond the standard model. All you need is a new force at the sub-giga electron volt scale with mass carriers of about, with the mass of the carrier for the force carrier of about MeV. With that, you can get these huge cross-sections. So only if you believe that new physics can only be found in the scale of TeV, then this seems kind of crazy. But there's a lot of people and a lot of models that think it's actually possible. I mean, there's a lot of dark matter models these days that predict self-interactions. So if the cross-sections are this strong, the centers of dark matter halos, where the velocity dispersions and the densities are high enough for the interaction rate to be in the order the whole time, then you will get low density cores, near spherical cores. You will get some substructure evaporation, and in merging systems, the drag of the dark matter experience will be different than that of the collisionist galaxies. So you will get some offsets between the surface mass centroids and the galaxy centroids. So that's our phenomenology. It's a rich phenomenology that will affect systems at all scales, from tiny dwarf spheroidals to huge merging galaxy clusters. But in order to put constraints on the cross-section, you need to have reliable predictions of what are these core sizes, these shapes for a given self-interaction cross-section. The most reliable predictions come from cosmological simulations, and there was a large effort to constrain the dark matter cross-section in the early 2000s, but the simulations didn't really have the sophistication technology to make reliable predictions across a wide range of halo masses. So because of that, the stringent constraints that came for SIDM that totally knock out SIDM in the early 2000s actually came from analytic estimates that made some assumptions that they were not confirmed by simulations. For example, Miraldes could in 2002 look at the surface density shape, the ellipticity of the surface, the projected surface density of this cluster right here. And she said that in order for there to be a non-circular symmetric surface density at radius greater than 70 kiloparsecs, under the assumption that the ellipticity will be completely zero, so completely circular, whatever the interaction rate were in the order of the whole time, then you will get that the limits for the cross sections will be below 0.02 centimeters squared per gram, which will be practically completely uninteresting for astrophysics. This wouldn't produce any cores at all in dwarf galaxies or nothing. So this completely knocked out SIDM in the early 2000s. And it wasn't until about 10 years later that we say, okay, well, this assumption hasn't been verified by simulations. There hasn't been robust, reliable predictions on this for simulations. Simulating SIDM is not an easy thing. It's tricky because you can use the two limits that we're used to. We can try to treat dark matter as a collisionless particle, as a collisionless system, not as a fluid. For these cross sections, they're right in between. So these are limits of the Boltzmann equation. And if you want to have a self-consistent algorithm, you have to derive it straight from the Boltzmann equation. That's what we did. And we implemented our algorithm in Gadget 2. And so we have a new set of simulations, of cosmological simulations, some zoom simulations, some full box simulations. This is just an example of a Milky Way-like halo with CDM and SIDM with 1 centimeter squared per gram. You can see lower central phase space densities and a little bit more spherical, but not much. So the time limitations here, I'm only going to provide you with a summary of our results. When we look at the core sizes and central densities of our sample of simulated halos, we found that for cross sections of 1 centimeter squared per gram, you will have core sizes that were just too large and central densities that were just too low as compared to observations across all scales. However, for cross sections around 0.1 to 0.5 centimeters squared per gram, it will not only will be allowed by observations, but actually these cross sections will be able to produce the core sizes that you will need in LSBs and dwarf galaxies, for if there is actually some cores there, as suggested. So that's from core sizes and central densities. In terms of shapes, we revisit this analysis, and we actually look at the projected densities on our cluster size cluster size halos from our simulations. And what we found is that actually cross sections of less than 1 centimeter squared per gram will be completely in agreement with observations of shapes and of clusters. In terms of substructure, as I told you, actually SIDM turned out to be really bad at deploying substructure. And what we find is that if you look at when the virial radius, subhelocons are identical to CDM. It's only when you go to the inner regions of the halos that you start seeing some depletion of subhalos. But it's small. We see, like, if you look at the inner 8, so within half the virial radius, you only see a difference of about 10 to 15%. Let me show you this explicitly. This is the subhalo Vmax function for a Milky Way-like host. It's a function of Vmax. And this is for different dark matter models. I just wanted to focus on the green dash and blue dash lines, which sit right on top of the solid line, which is CDM. Blue dash and blue greens are SIDM with 0.1 and 0.1 centimeters squared per gram. And they're just right on top of each other. This is within one virial radius. You see no difference on the subhalo Vmax function. Let me just flash really quick. This is the central densities we get for our sample of halos as a function of Vmax. And what I want you to see is that there is a large scatter. SIDM predicts a large scatter up to a factor of 3, which is probably incomplete. When we have more simulations, this will be better determined. But it's one of the predictions of SIDM to have large scatter on these central densities. Now, to constrain SIDM from central densities and cores, you need variance. We know that variance can really have an effect of the central densities of halos at some scales. So the core sizes, the central densities may change once you add variance, and it's going to be really hard to disentangle like the effect of variance and the effect of SIDM. So we believe that probably, eventually, if possible, it's going to be hard to constrain better SIDM with core sizes and densities. But a better route could be merging clusters. So for merging clusters, if SIDM interacts, you will expect an offset between the dark matter centroid, well, the bulk of the mass centroid, and the centroid of the galaxies. And there's a large sample of observations of merging galaxy clusters. And now we need to catch up with the simulations. There's really a lack of merging clusters of simulations, even in CDM, let alone for SIDM. And in order to really measure, determine probe SIDM in the order of 0.1 to 1 centimeter squared per gram, you will need a large sample of simulation and observations. And that's the effort that we're doing with the merging cluster collaboration between UC Irvine, members of UC Irvine, UC Davis, and some other institutions. So I'm over time, so I'm just going to leave you with my conclusions right there and take questions.
There's two pieces of evidence that there's a great deal of substructure in dark matter halos on the scale of less than a tenth of the virial radius. In fact, much less than a tenth of the virial radius. One is that at the Einstein radius in lensing galaxies, we see these radial quad flux anomalies. And that strongly suggests that there's a great deal of substructure at the scale of 10 to the 7 that creates solar masses, very close into the center. And the other is these streams of stars from breakup with small galaxies.
Yeah.
And those are as close as a few kiloparsecs away from the sun. So again, within 10 kpc at the center of a galaxy. Last I heard, talking to James Bullock, you don't have the resolution to go there.
Yeah.
But that figure you showed, this one there, was very impressive. If you're actually able to resolve down.
Yeah, we are able to resolve up to this Vmax, but this is when looking at everything with the virial radius.
What if you look in really close to the center?
We don't have, we can't go that close as,
But if you look at different radii,
and we are actually, we have some relaxed cluster simulations with SIDM in which we have better resolution, and we're doing this and all in the context of lensing, and we're going to get a paper soon on that and compare CDM and SIDM models, and some other models actually.
If you can just look at several different radii, you start to see a deviation from cold dark matter at the same high resolution. That would be an indication that when you extrapolate into the center, you're going to be in trouble.
Yeah. Let me show you really quick.
All right, let's have one more question.
Can I just ask quickly, so when you think about dark matter going through caustics, so for a short time you get very high density, high velocity dispersion, have you sort of played through whether your interactions thermalize dark matter in caustics?
Wait, can you repeat the question?
So if your dark matter is sort of falling into a potential well, and as it sort of turns around, really bunches up in physical space, and you get a very narrow structure. At the same time, because phase-space volume has to be conserved, the velocity dispersion goes up. So both things are actually, they go into the scattering cross-section. So in some sense, you could have a thermalization quite locally at this location. I think it's unlikely. I was just curious what you thought about it.
Yeah, I mean, I haven't really.
Must be following the particles through that, so you can actually check.
I mean, yeah.
In the simulations, you never sample that. You have so few particles sampled in caustic.
If they do it by your method, they see in the meeting.
Yeah, I could benefit from your method, even this idea. Anyway, just showing you for different halo masses when the half of the virial radius and when one virial radius. And you see the differences are so small. This is for 1 centimeter squared per gram. We're thinking that if something SIDM has to be between 0.1 and 0.5 centimeters squared per gram, the lines that are right on top of each other is for 0.1. So far, looking at smaller radius, we don't see any difference. Of course, we will have to go to a smaller radius.
All right, thank you.